Hi guys, today we're going to talk about geometric sequences versus exponential functions. Let's take a look at the first example. A ball is dropped from a height. After the first bounce, the ball was 18 feet above the ground. After each rebound, the ball rises to a height of 2/3 that from which it fell. Write a list of a geometric sequence that shows the height of the ball for the first 4 bounces. Question, it says after the first bound, the ball was 18 feet above the ground. So 18 is going to be the first term. The second term is going to be after the second bounce. After the second bounce, it says in the question that the ball rises to a height of 2/3 of the first one. So that means that we're going to have to multiply 18 by 2/3 because the height after the second bounce is 2/3 of the previous height. So that's going to be 2/3 times 18, which is 12. The height after the third bounce is going to be, again, 2/3 of the height of the second term or second bounce. So that means I'm going to have 12 times 2/3, which is 8. The height after the fourth bounce is going to be, again, 2/3 of the previous height, which is 8. 2/3 of 8 is 16/3, which is approximately 5.3 repeating. The next question, it says, identify the first term and the common ratio, R, in the sequence. So the first term in the list is 18, and that's going to be the first term. And the common ratio, which is the number that we kept multiplying by every single time to go from one term to the next, is 2/3. Write a geometric sequence to describe the height of the ball after each bounce. We know that we have a formula for the nth term of the geometric sequence, which is a sub n equals a sub 1 times r to the n minus 1. And we said to write the geometric sequence, all we need is to find the two values, which are the first term and the r, which we already have. So now the nth term equation is going to be a sub n equals, the first term is 18 times r, which is 2/3 to the n minus 1. In the next question, it says, fill the table of values that express y is the height of the ball after x number of bounces. So x is going to be the number of the bounces, and h is going to be the height. So after the first bounce, we know the height is 18. After 2 bounces, the height is 12. After 3 bounces, the height is 8. And after 4 bounces, the height is 16/3. Now the question is asking you to graph the table. So to graph the table, we have to put the numbers on the x-axis. We have numbers going from 1 to 4. So I'm going to do 1 here, 2 here, 3 here, and 4 here. The y-axis is labeled for us. All we need to do now is to graph. 1, 18 is right here. 2, 12 is right here. 3, 8 is right here. And 4, 5.3 is right here. So if you look, this is not exactly a straight line. but it looks like it's an exponential function. So it's not a linear function, it's an exponential function. Now we know that the equation, it says write an equation that would determine the height of the ball, y, after x number of bounces. So now all we need to do is to think about the exponential equation that goes with this graph. We know that exponential equations have the formula y equals a times b to the x. And just to remind you, a is the initial value and b is the the exponential factor. The exponential factor that we have here is the number that we keep multiplying going from one y value to the next. And the number that we keep multiplying going from one y value to the next is 2 over 3. So 2 over 3 is going to be the factor. Now, we need the initial value. The initial value happens when x equals 0. So it's going to be the value before x equals 1. Let's take a look at the y value for x equals 1. It's 18. That means there was a number for x equals 0 that I had to multiply by 2 over 3 to get 18. Now to get that number, all I can do is to do the opposite and divide 18 by 2 over 3. And when you divide 18 by 2 over 3, you get 27. And that's the initial value. So the initial value is going to be here, which confirms that this graph looks like an exponential decay function. If you look at the equation, the nth term equation that we had for the sequence, and the exponential equation, you will see that both have one thing in common, which is the common ratio and the exponential factor. So the common ratio in the geometric sequence is equal to the exponential factor in the exponential equation. They're both the same. Now do number 2 by yourself. In question number 2, during a flu outbreak, a hospital recorded 20 cases during the first week, 50 cases during the second week, and 125 cases during the third week. Write a list of geometric sequence to model the population of the flu outbreak. So, during the first week, we had 20 cases. During the second week, we had 50 cases. And during the third week, we had 125 cases. So this is a sequence. The first term in this sequence is 20. And because it says it's a geometric sequence, we know that we need to find R. And to find R in this geometric sequence, all we need to do is to divide the second term by the first term, or the third term by the second term. 50 divided by 20 is going to be 5 over 2, or 2.5. 125 divided by 50, that's the third divided by the second, is going to be the same thing. So every single time we're going to one term to the next, we are multiplying by 2.5. Now that I have the first term and the R value, we can write the nth term rule for the sequence. So we have a sub n. We're going to follow the formula, a sub 1 times r to the n minus 1. That means a sub n equals 20 times 5 over 2 to the n minus 1. And that's the nth term rule for the geometric sequence. Now, let's fill up the table. We have week 1. During week 1, we had 20 cases. After 2 weeks, we had 50 cases. After 3 weeks, we had 125 cases. Now we're going to graph these values. If you look at the graph, you'll see that we need to label our x-axis with 1, 2, 3. So I'm going to put 1 here, 2 here, and 3 right here. And I'm going to have to label my y-axis. So I'm going to go by 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. Now let's graph. 120 is right here. 250 is going to be right here. And 125 is going to be right here. So again, this looks like an exponential function. It's a growth exponential function. And we need to write the equation for this exponential function to determine the number of patients n after W number of weeks. So n is y and W is x. We know the formula for the exponential function equation, which is y equals a times b to the x. In this case, we have y is n, and then x is W. To go from one y term to the next, we had to multiply by 2.5 or 5 over 2. So that's going to be that factor. And the initial value is when x equals 0. That means it's the value before x equals 1. For x equals 1, the n value is 20. For x equals 0, there is a number for which if we multiply it by 2.5, we get 20. That's why I'm going to have to do the opposite. Instead of multiplying, I'm going to divide 20 by 2.5 to find that n value. 20 divided by 2.5 is 8. So the initial value is going to be 8. And that's the equation. And 8 is right here. On the graphs, we saw that the graph in these two models looks like an exponential function. So we can say now that geometric sequences are examples of discrete exponential functions. They are the same. The difference between the geometric sequence and an exponential function is that when we have a geometric sequence, we have a discrete variable, which is a variable that cannot be represented by real numbers. It can be represented by whole numbers, integers, natural numbers, but cannot be represented by real numbers. When we have an exponential function, that means we have continuous variables. We have variables that can be represented by real numbers. So when we have a discrete variable, the example can be represented by geometric sequence, and the graph is going to be represented in dots. And when we have a continuous variables, that means that we have an exponential function where we connect the dots. So connect the dots for the continuous variables, and disconnect the dots for a discrete variable. So in the first example, let's take a look at the variables in the first example. We have the number of bounces and the height of the ball. The height of the ball is a continuous variable. The number of bounces is a continuous variable. That means that these dots can be connected together. And the best way to represent this situation is going to be using the exponential function. In the second example, we have the number of weeks, which is a continuous variable, but the number of patients is a discrete variable that cannot be represented by all real numbers. It can be represented only by whole numbers. That's why these dots need to stay disconnected. And the geometric sequence is going to be a better representation of this example.